Alright everybody, we are heading back into section 7.4, looking at integration of rational functions by partial fractions. So in this section we're going to be looking at yet another type of more complicated function that we can simplify and integrate using a new technique of integration. So we're looking at the method of partial fractions today. So the idea behind partial fractions and breaking down rational functions into simpler parts is that it's going to be easier to integrate separate smaller functions than to integrate one big one. So if we have this pair of rational functions here, let's go ahead and combine those into one rational function. So put them over a common denominator of x minus 1 times x plus 2. So we're going to get 2 times x plus 2 minus 1 times x minus 1 over the common denominator. So that gives us, let's see, 2x minus x is just x, and then 4 plus 1 is 5. So we get x plus 5 over x minus 1 times x plus 2. And then we can FOIL out that denominator. So we get x squared plus x minus 2. Okay, and the purpose of doing this is more just for the exercise, because if we wanted to integrate, so to integrate the function x plus 5 over x squared plus x minus 2 dx, integrating this as is would not be an easy task, but if we can manipulate it algebraically and backtrack our way to get it into two simpler functions, we can integrate those instead, and then that's going to be easier for us to work with. So we have 2 over x minus 1 minus 1 over x plus 2 dx. Those are both integrable, and they both involve the natural log. So this becomes 2 ln absolute value of x minus 1 minus ln of absolute value of x plus 2 plus c. So fair warning, you will see a lot of natural logs popping up in this section because you get a lot of these rational functions that look like the derivative of a natural log function. Okay, so consider an arbitrary rational function f of x equals p of x over q of x. If f is improper, okay, and so that is to say the degree of p is higher than the degree of q, so an improper fraction, right, the numerator is bigger than the denominator, we must use long division. So when you're solving these types of problems, we first need to check whether or not the degree of the numerator is higher. If the numerator has a higher power, we need to use long division until it doesn't, basically. Okay? And that's going to then allow us to apply this type of method and then integrate. So let's look at this example here. So find the integral of that rational function. Well, notice the degree of the numerator is 3, the degree of the denominator is 1, so we do need to use long division here. So if you haven't done long division in quite a while, this is going to be a good refresher for you. So I have x cubed plus x being divided by x minus 1. I'm going to put a placeholder here of 0x squared plus x. Just so that I can make sure to keep my places kind of in order here. So what we do to do long division, you take the leading term of this one and you divide it into that one. Okay, so the x cubed divided by the x is going to be x squared. And then you take whatever term you get here and multiply it by this. So that's going to be x squared times x is x cubed. X squared times negative 1 is negative x squared. Whatever you get, subtract. And then the idea is that those will cancel to 0 every time. And then now we get 0 minus a negative, so that's a plus. So we just get x squared, and then bring down whatever the next term is. Okay, and then repeat the process again. So the leading term here goes into this one, so that's just x squared over x is just x. Okay, and then do the same thing. Multiply this by that, by the x minus 1. And that's going to give us x squared minus x, and then subtract. So we get 0, and this gives us 2x. Again, x goes into this. That's just a 2 now. So we get 2x, and then minus 2. Okay, and then subtract that, so it just leaves us, with a positive 2 when all is said and done. Okay, I mean, you can put the plus 0 as a placeholder if you like down there. So you get 0 plus 2. Now, what we have done here is we have divided this, so we've put it into a new form. This rational function can be rewritten as x squared plus x plus 2 with a remainder of 2 over x minus 1. Okay, so there's a 2 left over that we weren't able to cleanly divide away. So, but this is going to simplify this immensely. So we get x squared plus x plus 2, and then plus the remainder over the divisor there. So we get this simplification. And this we can now integrate just using our previous Calc 1 methods. So we get x cubed over 3 plus x squared over 2 plus 2x plus 2 ln of absolute value of x minus 1 plus c. Alright, so you'll see we'll be doing a couple more examples where we're going to have to incorporate long division into it. Just looking through to make sure we're going to do that again. Yeah, so there's another one that we're going to see that a little bit later. So if you are rusty on your long division, I would just go in and maybe practice it a couple times. And when you go through the homework too, you'll get some practice with it. But this is really the only type of circumstance where you're going to encounter that. So just something for you to be aware of. So when we're dealing with this method, we need to factor q of x as much as possible. So q of x is that denominator we saw up here, right? P over q. We need to factor it as much as possible and then express the proper rational function r of x over q of x as a sum of partial fractions. So r of x over q of x, this is a proper rational function because it's not improper anymore. So this is after long division. So after long division, of course long division is not always necessary, so I'll just add if necessary. Okay. So whenever we get terms in these partial fractions, what we like to call them, you're going to get something that looks either like this or something that looks like this. So you're going to get either a linear factor in the denominator or a quadratic factor in the denominator. And we're going to look at a few different cases of different types of scenarios you can see here. So we have case 1. So case 1 says, what if the denominator q of x is a product of distinct linear factors? So we have linear factor times a linear factor, etc., with no repeated factors. Then there must exist constants a1 through ak such that this fraction r of x over q of x is a1 over a1x plus b1 plus a2 over a2x plus b2 plus dot dot dot. So just kind of etc., all the way up to the kth term. Okay, so if we are able to factor that denominator into non-repeating linear factors, then you can split it up in this form. So basically we get a new fraction for each linear factor. Okay, and then our job will be to find out what these constants are, and then once we have those, this is going to be easier to integrate than the original was. Okay, so that's our goal here. Get it into a simplified form so that we can integrate it more easily. Okay, so first thing with this example, first thing that we should note, look at the degree. The numerator is squared, the denominator is cubed. So this is good. So note, so in parentheses, note the degree of the denominator is larger, so no long division needed. Then all in one line, there we go. So that's good. That saves us a little bit of work. Now, our next job is to try to factor that denominator as much as possible. So the 2x cubed plus 3x squared minus 2x. So we're going to factor it. So notice there's a factor of x in the whole thing. Okay, so actually let me set this up properly here. So 2x cubed plus 3x squared minus 2x. It's going to be x times 2x squared plus 3x minus 2. So the question is then, is that quadratic factorable? It turns out it is, so you can try it through a little trial and error here. You get 2x minus 1 and x plus 2. So what we've just figured out is that we have 3 distinct linear factors. Okay, so 3 distinct linear factors. So the partial fraction decomposition has the form I'm going to put it right there. Actually, keep it over here. So we have 3 distinct linear factors. That's a linear factor, that's a linear factor, that's a linear factor. They're non-repeating. So that means our partial fraction decomposition, and this is just kind of the fancy term, decomposition, meaning we're breaking it down into smaller pieces. So x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x equals a constant over the first term plus a constant over the second term plus a constant over the third term. Okay, so I used a, b, and c. You can use any variable you want, but typically a, b, c are the common ones. And what we need to do is I want to integrate this function instead of this one, because this one is very complicated and doesn't look like I could integrate that very easily. So I want to integrate this side instead, but to do that I need to find what a, b, and c are. Okay, I need to find those constants to be able to do that. So just make a note. We need to find a, b, and c. Okay? If we can find a, b, and c, then we integrate. So this is where most of the work from the problem is going to come from, because we need to solve for a, b, and c. So we're going to basically end up setting up a system of equations here. So let me go ahead and just rewrite this denominator down here in terms of the factors. That'll make this a little easier to see. So there's the 2x minus 1, there's the x plus 2. Okay, so what we're going to do is we're going to multiply by the least common denominator, the LCD, which in this case is going to be the x times the 2x minus 1 times the x plus 2. And we're doing this to eliminate the denominators, because it's going to be a lot easier to solve this if we don't have to deal with fractions. Even though it's kind of ironically the name is the process is partial fraction decomposition. So multiply both sides by that LCD. So on the left hand side we have x squared plus 2x minus 1. On the right hand side we have a times, so the x cancels with this one, so we have both of those left over. So we get a times 2x minus 1 times x plus 2 plus b times the terms that don't get canceled, so that's x and x plus 2, plus c times the terms that don't get canceled, so x and 2x minus 1. Okay. Once we set it up this way, let's go ahead and just multiply everything out, okay, so that we can do a little regrouping in just a minute. So this side, I'm going to leave this side alone throughout most of this simplification. So we're going to have 2x squared plus 3x minus 2, all of that times a. So we're going to have 2ax squared plus 3ax minus 2a. Okay. And then for the b terms, we have plus bx squared plus 2bx plus 2cx squared minus cx. Now, you might think I want to group up in terms of a, b, and c. However, these were already grouped in terms of a, b, and c, and that's not going to help us. What we're going to do is group by power. Group by the power. So the left side is going to stay the same. So x squared plus 2x minus 1 equals, so I'm going to group all the x squareds together. I'm going to group all of the x's together and all of the constants together. So we're going to have 2ax squared plus bx squared plus 2cx squared, and then plus the x terms, so 3ax plus 2bx minus cx, plus the constant terms, which there is only one, it's just minus 2a. Okay, that's the only term that doesn't have an x attached to it. And then factor out that common power. So we're left with 2a plus b plus 2c all times x squared plus 3a plus 2b minus c all times x, and then minus 2a. Okay, so we've done a lot of algebraic work here. And remember, our goal is still I want to find a, b, and c, so that I can integrate this function instead of the complicated one. So, what we can do now is we can say if this side is truly equal to this side, that means that the x squared term has to be the same as this x squared term. This x term has to be the same as this one, and this constant term has to be the same as this one. So what we're going to do, the terminology we use is it's called equating the coefficients. So we're going to equate the coefficients. Okay. Because again, if I truly want this side to be equal to this side, well then if the coefficient on x over here is 2, then that means this number is going to have to be 2 in order for these two things to be equal to each other, right? And this one has 1x squared, so this is going to have to equal 1, right? And this is -1, this is going to have to equal -1. That's the only way these sides are going to be equal to each other. And this argument gives us exactly what we need to solve for a, b, and c. So, start with the x squareds. So I know that on the right-hand side I have 2a plus b plus 2c. And that has to equal the coefficient on the left, which is 1. Okay, then I have 3a plus 2b minus c must equal 2, because that's the coefficient on the x. And then I have negative 2a must equal -1. Okay. And then we solve this system of equations. I'm not going to go through this entire process with you guys. It is expected that by the time you reach Calc 2, you know how to solve a system of equations. But I can give you just the quick down low on this. Solve this one for a, plug it into these two, and then solve what's left for b and c. A system of two equations and two variables, you can use either substitution or elimination to do that. But if you do, you will get the following values. So solve the system of equations. You're going to get a is 1/2, b is 1/5, and c is -1/10. Okay, so we did a lot of work to get down to the a, b, and c values, but just bear in mind all the work we did was algebra. And by doing all this algebra, we have now made it possible to integrate this complicated function, which we would have had no hope of integrating before this. So now, the values we get for a, b, and c get plugged in to these functions, to these fractions. So, let me just do this right here. Okay, so we have the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx equals, okay, so again we're using this formula up here. So we found that that value was 1/2, this value was 1/5, and this value was -1/10. So I'm going to use those. So we're going to get 1/2 times 1 over x plus 1/5 times 1 over 2x minus 1. And we're going to get minus 1/10 times 1 over x plus 2 dx. And each of those terms can then be integrated. So we're going to get 1/2 times ln absolute value of x plus, now this would be 1/5, however, in taking the antiderivative of this, we have to incorporate the chain rule because it's 2x minus 1. So you would have to do a u substitution here, and then your du would end up being 2dx, and then you would divide by the 2. So you would get an extra factor of 1/2 there. I'm not showing all of that work. I'm calling it kind of a mental u substitution, but that 1/2 ends up turning this into a 1/10. And then times ln absolute value of 2x minus 1, and then minus 1/10 times ln of absolute value of x plus 2, plus the arbitrary constant c. And so that's what we get for our integral. Okay, so as you can see, these partial fraction problems, you're going to need probably big pieces of paper to do these, because they do take up quite a bit of space. But in terms of the calculus that we did, it was just from here to here. That was the only calculus we did in this entire problem. But that's why we need these algebra skills to set us up well to do the calculus. So if you look back at what all we did, okay, we factored a polynomial, we set it up using the formula we were just given, right? The formula for the partial fraction decomposition. We did multiplication. We multiplied out factors more. We did grouping. We factored. And we solved a system of equations. And we did all of that to get back into an integral that we could then solve in one step. Okay, so we're putting in our time algebraically here, and that's going to allow us to solve simpler integrals.